So far, we learned the arc length of y equals to f of x if f has a continuous first derivative on the interval a and b. The length of the curve from the initial point A to terminal point B is the definite integral a to b of square root of 1 plus f prime of x to the second dx. Sometimes you have to isolate x. Sometimes you have to write x in terms of y. In that case, if x is equal to g of y and it has a continuous first derivative on the closed interval c to d, then the length of the curve from the initial point g of c, but now you're working with your y, so you're going to focus on your c to this terminal point g of d, and since you're working with your y, d is the definite integral from c to d of square root of 1 plus g prime of y to the second dy. Please note that this exponent only belongs to the derivative. You are not raising the whole thing to the second power, just the derivative itself. Very well. Example for you. Question says, find the length of the curve y equals to ln of x plus square root of x squared minus 1 on the closed interval 1 to square root of 2. Okay. Y is equal to ln of x plus square root of x squared minus 1. Remember the definition of ln of x, which is basically log with base e of x. Our goal is to isolate our x because it makes the derivative and raising it to the second power and calculating the length a little bit easier for us. So e to power y is equal to x plus square root of x squared minus 1. So in general, if y is equal to ln of x, then x is e to power y. This is what we are having here. Or if y is equal to ln of u is e to power y. E to power y can be written as x plus square root of x squared minus 1. We want to get rid of this square root, so we're going to bring x to one side next to e to power y, and on the right hand side, we get square root of x squared minus 1. Now, if you raise both sides to the second power, e to power 2y minus 2 e to power y times x plus x squared becomes x squared minus 1. So what we did, we just took this guy and raised it to the second power, both sides. To the second and to the second. But please note that if you have a minus b to the second, this is a squared minus 2ab plus b squared. In that case, we have e to power y minus x to the second, which is e to power y to the second minus 2 e to power y times x plus x to the second. E to power y to the second is e to 2y. The rest are just copying down from the formula that you have, negative 2 e to power y times x plus x squared. On the right hand side, exponent 2 and the radical, they get cancelled out. So you end up with x squared minus 1. Now, x squared and x squared, on both sides, they get cancelled out. So e to power 2y minus 2 e to power y times x is negative 1. Well, in turns, you can write this as e to power 2y plus 1 equals to 2 e to power y times x. So you're basically bringing this guy to the right-hand side and this number to the left-hand side. Why? Because that's how we can isolate x. You just need to divide everything by 2e to power y and then simplify. X becomes e to power 2y plus 1 divided by 2e to power y, because these two, they get cancelled out, and you can isolate x on one side. So from y to be ln of x plus square root of x squared minus 1, we got x to be e to power 2y plus 1 divided by e to power 2y. We can also simplify this guy further. Why we are doing that? Because it makes it much more easier to take the derivative. So let us continue. So far we saw that x is equal to e to power 2y plus 1 divided by e to power 2 times e to power y. Well, you can simplify this further. Why? Because you can just write this as x as a function of y, which is e to power y plus e to power negative y divided by 2. The algebra behind this part is very easy. You're basically dividing both the numerator and the denominator by e to power y. So e to power y and e to power y, they get cancelled out. And then on the numerator, e to power 2y divided by e to power y becomes e to power y. And 1 divided by e to power y is e to power negative y. Now, if you take the derivative of x, g prime of y is e to power y minus e to power negative y divided by 2. Very well. Remember the length formula. Now that you have x in terms of y and you found the derivative of x, you just need to plug that into the formula and calculate the length. This is the definite integral between c to d of square root of 1 plus g prime of y to the second dy. So L is the definite integral 0 to ln of square root of 2 plus 1 times the square root of 1 plus g prime of y to the second dy, which in turn can be written as square root of 1 plus, wherever you see g prime of y, you're going to write down e to power y minus e to power negative y divided by 2, and then you raise it to the second power. Then you take the integral with respect to y. So far, we saw that the definite integral is 0 to ln of square root of 2 plus 1, and you have square root of 1 plus e to power y minus e to power negative y divided by 2 to the second. Then you take the integral with respect to y. But remember that e to power y minus e to power negative y divided by 2, doing a little bit of algebra, raising to the second power, is taking the numerator, square it, taking the denominator, 2 to the second, which is 4, and it becomes, since the numerator is e to power 2y minus 2 e to power y times e to power negative y, which is 1, plus e to power negative 2y. So we're going to use these and write them inside the radical and simplify as much as we can. This becomes the square root of 1 plus e to power 2y, so this guy, to the second, which we wrote down as simplified version. Down here, they are the same thing, and this is the algebra behind it. Taking the integral with respect to dy, but before taking the integral, let us try to simplify this further. If you take the common denominator 4, it becomes 4 plus e to power 2y minus 2 plus e to power negative 2y, then dy. But 4 and negative 2, well, if you combine these, you get positive 2. What happens is that inside your radical, you have e to power 2y plus 2 plus e to power negative 2y divided by 4. This guy can be written as, well, inside your radical, e to power 2y plus 2 plus e to power negative 2y can be combined in just a binomial, which is e to y plus e to power negative 2y to the second, and then you take the integral of it. So on your numerator, the square root and exponent 2, they get cancelled out, and you end up with e to power y plus e to power negative y, and a half goes outside the integral. This integral is super easy to calculate, everybody. So remember, we cancel out these two. That's how you got rid of the radical. This in turn is a half e to power y minus e to power negative y, and y ranges between 0 to ln of square root of 2 plus 1. Just substitute the upper bound, substitute the lower bound, and simplify to get 1. What's the algebra behind it? So you have a half, and you have e to power ln of square root of 2 plus 1 minus e to power negative ln of square root of 2 plus 1, and then you substitute 0 as well, which gives you 0, so minus 0. But remember that e and ln, they get cancelled out, so you have a half square root of 2 plus 1 and minus, so here you have the negative sign. You can take this negative sign and write this as the exponent of square root of 2 plus 1. So you get minus 1 divided by square root of 2 plus 1, and then this a half belongs to both of them. You can take the common denominator. This is a half. And if you take the common denominator, which is square root of 2 plus 1, here you have square root of 2 times square root of 2, which is 2, square root of 2 times 1, square root of 2, then plus square root of 2 plus 1 minus 1, right? So these two, they get cancelled out, and these two simplifies into 1, because here you can write it as 2 parentheses 1 plus square root of 2 divided by 2 times square root of 2 plus 1. Can cancel out 2 and 2. Can cancel out 1 plus square root of 2 and square root of 2 plus 1. That's how you end up with 1. So the length of this curve is equal to 1.